Hello my dear scientists and nuclear engineers. So this is continuation of Glasstone and Sesonske book. In the previous class what I discussed you understood it seems. I will remind what I actually taught in the last two classes. The fission, how fission occurs, how much energy releases. Amount of energy released in the fission reaction you can calculate in two ways. First one is binding energy per nucleon of uranium-235 is 7.6 mega electron volt per nucleon. So after fission occurred, the fission products binding energy per nucleon, it is around 8.5 mega electron volt. 8.5 mega electron volt minus 7.6 mega electron volt, that is 0.9 mega electron volt into number of nucleons. How many nucleons are there in uranium 235? 235 are there. So 0.9 mega electron volt into 235, that is approximately equal to 200 mega electron volt. So in fission reaction approximately 200 mega electron volt energy will be released. Another method, mass defect. Uranium 235 undergoing fission product 1 plus fission product 2 plus 2 neutrons. So difference in mass of uranium 235 minus sum of the masses of fission product 1 plus fission product 2 plus 2 neutrons. This mass difference, that is mass defect, into C square, that is the amount of energy released in the fission reactions. This you understand. Now we will compare how much uranium 235 power produced equivalently how many kgs of coal produces same power. Okay, so simple example, 1 kilogram of uranium 235 how much power produces, same power to produce by coal, how much coal is required, that we will discuss now. Okay, this is also part of the syllabus in Glasstone and Sesonske book. Very simple calculations I will tell you. 1 uranium 235 undergoing fission producing 200 mega electron volt. 1 carbon 12 atom on combustion, it is producing heat 4 electron volt. This is 200 mega electron volt. Coal is 4 electron volt, just 4 electron volt, that is 200 mega electron volt. How to calculate the relation between amount of U235 and amount of carbon 12? This 200 mega electron volt produced by, for calculation only I am telling, uranium 235. The 235 mass number means number of proton plus neutrons. So 200 mega electron volt divided by 235. Okay, that is nothing but amount of energy released per nucleon for uranium. Similarly for carbon 12 also. 12 is the molecular weight or mass number. 12 means 6 proton plus 6 neutron, that you know. So carbon 12 on combustion producing 4 electron volt. 4 electron volts divided by 12. This is also amount of energy released per nucleon. For uranium 235, 200 mega electron volt divided by 235. For carbon, 4 electron volt divided by 12 grams. 12. Now you take the ratio of this. You can very well find out how much coal is required. Okay. So I can do simple division. No, this 200 mega electron volt divided by 235 is one quantity, divided by this one 4 by 12. You will get the value is like this. Around 1 kg of uranium 235 is equivalent to 2550 metric ton 2550 metric ton. Ton means 1000 kg. Okay, so 1 kg of E235 equivalent to 2550 metric ton. That is the equivalence. You understood, no? So approximately 2500, you can call approximately 3000. So you can call 3 million times. It is 3 million times. Simple rounding off. If you tell, if somebody asks approximately what is the order, 1 kg of U235 equivalent to how many kg of coal, it is approximately 3 million times, you can say 3 million times. But exact value if you want, around 2550 metric ton, 1 kg of U235. I am telling U235, it is completely fissile material. Natural uranium is different. Natural uranium contains 0.71% only. So after that you can calculate 1 kg U235 available, how many kgs of natural uranium, that you can calculate. This is clear now, you understood. Okay, now what we should know, this carbon atom on combustion, it is releasing the heat 4 electron volt and releasing carbon dioxide also. It is releasing carbon dioxide also, which we don't want. In fact, which we want, we must try to avoid carbon dioxide emission, but it is happening when you are using coal. Now we will calculate how much carbon is burning, how much carbon dioxide is releasing. Very simple calculation. Carbon 12 grams I am calling as a molecular weight. It is a empirical number. It is a particular number. It is weighted average type you take, or it is a fractional number, you can say. So carbon 12, matlab 12 grams of carbon also you can say. 12 is the molecular weight also you can say. Now I am considering 12 grams of carbon. After combustion, carbon dioxide is released. Okay, carbon C plus O2, CO2. Carbon is 12 grams. That's what fuel I am supplying. Carbon dioxide is coming. This is 12 grams. Carbon dioxide means carbon is 12 plus oxygen is 16 plus 16. 2 atoms are there, no? 12 plus 16 plus 16, 44. So 12 grams you are burning, 44 grams carbon dioxide is producing. Be careful what I am telling. It is 3.7 times. So carbon dioxide emission is 3.7 times the carbon burning. If you burn 10 ton of coal, 37 ton carbon dioxide produced. You got it, no? So simple, you can say answer if somebody asks how much equivalent means 3.7 times. Okay, that is answer. Now we will compare uranium-235. We are constructing a reactor which produces a thermal power. I am talking now a thermal power only. Thermal power of 1000 megawatt. One reactor I have constructed, I designed it, I constructed. It is producing a thermal power around 1000 megawatt. 1000 megawatt reactor operating one day. What is unit of energy? Okay, so, I think it is wrong. What is unit of power? Power means joule per second, rate of energy, rate of work done, that you know. So what is unit of power? I want energy. Energy equal to power into time. So watt into time. Time may be second, time may be minute, hour or day. So reactor is operating one complete day. So what is the power producing by the reactor? 1000 megawatt. In one day how much energy released? 1000 megawatt into day. Also you can do. Day also time, no? That is nothing but energy released. So 1000 megawatt reactor In one day it is releasing energy 1000 megawatt day. For that, how much uranium 235 you have to feed to the reactor? Because this reactor is producing power by using a nuclear fuel. 1000 megawatt day produced by the reactor in one day, it requires 1000 grams of uranium 235 produces 1000 megawatt day. Then 1 gram produces 1 megawatt day. You understand? Okay. Now we will compare this uranium 235 with the coal. Just now I told 1 kg of U235 is around 2500, you take it approximately 2500 tons. Okay. In one day, to produce 1000 megawatt day power, 1000 megawatt day energy in one day, I required how much coal? This is 1 kg, no? 1 kg into 2500. Matlab into you don't do. So 1 kg is equivalent to 2550 tons. So 2550 ton of coal is required every day. 1000 megawatt reactor, if it is operating one day, I am consuming uranium 235 of 1 kg. But for coal you need around 2500 tons. That much coal you have to burn. So how much carbon dioxide releases? Into 3.7 you have to do. So 2550 ton is a coal burned. So carbon dioxide released is into 3.7 you do. So that much carbon dioxide is releasing. So you can just comparing one thermal power station and nuclear power station. We can avoid carbon dioxide emission. The intention of this lecture is not downgrading or telling disadvantages of the thermal power plant. So far, thermal power stations are worked for the nation. Of course, we were getting electricity from the thermal power station. So the time we have the technology, the time we don't have that much knowledge in designing nuclear reactors and nuclear technology. So far, our country is served by thermal power station. But our policy is integrated energy policy. Ultimately, we have to serve for the country by integrating all possible technologies. Okay. Now our future plan is that carbon dioxide emission we have to avoid. This entire world, not only just particular our country, India, entire world is trying to go in that direction. The main intention is it should not affect much our environment. So for that power production, you switch over from thermal power station to nuclear power station. The first reason is we can avoid carbon dioxide emission. So that part. Now these things you understood very clearly. The next topic of the Glasstone and Sesonske, you can listen in the next coming topic, that is critical mass. Critical mass means how the fission reaction is happening. That part you understood everything. Okay, you have to maintain a chain reaction. To maintain the chain reaction, you need a sufficient nuclear fuel. I've given you 1 kg, you construct a reactor and produce the power. It's not so simple. So for everything, for design, you need a certain fissile material quantity and particular shape and particular quantity geometry, that's shape only. So the critical means chain reaction is sustained. That is critical. To sustain the chain reaction, we need a minimum quantity of uranium mass is required. I forgot to explain how 1 gram of uranium 235 will produce 1 megawatt day. 235 grams of uranium 235 contains Avogadro number of atoms. Avogadro number is 6.022 into 10 to the power of 23. So 1 gram of uranium 235 contains Avogadro number divided by 235. So you know number of uranium 235 atoms in 1 gram of uranium 235. For each uranium 235 undergoes fission, it will produce 200 mega electron volt. No? Now you multiply that number into 200 mega electron volt. Electron volt you convert into joules. 1 electron volt is equal to 1.602 into 10 to the power of minus 19 joules. So finally you will get the answer approximately equal to 1 megawatt day. What is meant by 1 megawatt day? Day is time, no? Watt is unit of power. So if you multiply power into time, you will get the energy. So day means 24 hours into 60 minutes into 60 seconds. You have to convert into seconds. Then only this answer will match. Okay? I think this is clear. Now we discuss about critical mass. This is one of the topic given in Glasstone and Sesonske book. Critical mass. Critical mass definition, first I will tell you in simplest manner. So minimum amount of uranium fuel required to maintain chain reaction or to maintain sustained chain reaction. Why we need a sufficient minimum? If it is less than that, what happens? That I will explain now. Okay? We know that in fission reaction, 2 or more neutrons are produced. If 2 neutrons produced, the 2 neutrons will go to the another uranium 235 2 atoms and 2 more fission should occur. 2 atoms, the 2 neutrons will become 4, 4 becomes 8, 8 becomes 16, becomes 32, becomes 68, 64, it will continue. It should keep on increasing. But it is not happening. Why? The neutrons which produced in fission not only going to the uranium 235 and undergo fission. What happens? Some neutrons may undergo radiative capture. That neutron may be absorbed in uranium 238, that will not undergo fission. Some fissile material, that is uranium 235, also will not undergo fission even though after absorbing the neutron. So that is the radiative capture. Apart from this radiative capture, the neutron will leak out of the fuel. It means what? You are taking some amount of uranium. If it has some particular shape of like a spear, you take 1 kg or some quantity of uranium fuel, you assume that some fission is happening inside the spherical ball. So what happens? The neutrons may come out of the spherical ball, they will go out of it. That is leakage probability. So there is probability of that neutron may go out of the fuel. The neutron will leak out of the fuel. If fuel is very, very small, this leakage probability is higher. Okay? So you have to increase the quantity of fuel. So increase the volume of the fuel, so that number of neutrons produced in the fission reaction may be sufficient to sustain the chain reaction. The first reason is you have to increase the number of neutrons. Why? Because some neutrons are going to capture as a radiative capture, some neutrons are leaking out of the fuel. So that is why we need to generate sufficient number of neutrons by increasing the quantity of nuclear fuel. Now it is clear, no? Okay. Then what is the order of this critical mass? Means what is the minimum quantity? you should use to sustain the chain reaction. So it varies from less than 1 kg to tons. Less than 1 kg of uranium fuel also you can make sustained chain reaction, and you may need sometimes 30,000 kg, 40,000 kg also. Depends on how much fissile content is there in that fuel. Already I told you, in the nature, the available uranium, 3 isotopes, out of them uranium 235, which is fissile material, which will undergo fission with neutron of any energy, high fission cross section is there, only 0.7 percentage. Means out of 1000 atoms, only 7 atoms are uranium 235. So natural uranium, if you use 1 kg, 2 kg, 3 kg, 4 kg, you cannot make sustained chain reaction. Then what we have to do? You have to enrich. Enrichment means what? What is meant by enrichment? Naturally 0.7 percentage is there, no? E235. I want to increase more than 0.7 percentage. How can you increase? Already it is available only 0.7 percentage in the nature. How can you increase? Can you insert E235? No. What you can do is, to increase the percentage of U235, there are 3 isotopes, 234, 235, 238. Uranium 238 is 99.28 percentage, very high. Now I will remove the uranium 235 atoms. Then what happens? The percentage of uranium 235 increases. This is called enrichment process. If you enrich this uranium 235 up to 90 percentage with less than 1 kg of uranium, which is 90% enriched, you can attain when uranium 235 is 90 percentage, less than 1 kg of that uranium fuel, which is 90%, we can maintain a sustained chain reaction. If it is natural uranium, we required around 30,000 kg, 40,000 kg of uranium fuel with 0.7 percentage. Okay, this is clear, you understand. Now another topic will move, nuclear fission reactors. We will design now reactors. The reactor design consists of a core. Core contains fuel and some moderator and some heat transport system. In the fuel fission reaction occurs, so fuel gets heated up, that heat we have to remove. So we have a heat removal system. This moderator, I am telling you, what is the use of moderator? Why we have to use the moderator? Moderator means what? Moderator, it is doing a function of slowing down the neutrons. In the fission, the neutrons produced are fast neutrons. The energy of fission neutrons are average 2 mega electron volt. Such a high energy neutron cannot maintain a sustained chain reaction with natural uranium fuel. So you have to slow down them. How can you slow down? You should allow these neutrons to collide with some atoms. So the neutron mass, it is similar to proton mass. So the mass of the target material or moderator should be near to the mass of the neutron, so that elastic scattering occurs, the energy transfer from the neutron to the moderator is very high, so that you can slow down the neutrons very quickly. So better moderator is light water or heavy water. What you have to take care when you are selecting moderator, the moderator should not absorb the neutron also. If it is absorbing the neutron is waste, because neutron should and must be absorbed in the uranium-235 to undergo fission reaction. So you have to see the two properties, that moderator should reduce the energy of the neutron very quickly. At the same time, it should not absorb the neutron. In that case, light water, heavy water, if you compare, heavy water is better than light water. Okay, heavy water is D2O, 1H2, one neutron, one proton is there in the deuterium. But in light water, H2O, hydrogen contains only one proton. But hydrogen absorb the neutron more than D2O absorb the neutron. So absorption cross section for hydrogen is more compared to deuterium. So out of these two, I can prefer deuterium oxide, D2O, that is heavy water. Okay, but there are certain reactors in which they are using light water also as a moderator. For that, we cannot use natural uranium as a fuel, because natural uranium contains only 0.7%, no, very less quantity of uranium-235 is there. So neutrons production also less. The neutrons will be absorbed in the water, light water. So हमको chain reaction sustain करने के लिए मुश्किल होता है. Then what you have to do? You have to enrich the uranium. You can use enriched fuel in the reactor in which we are using moderator as a light water. So all light water reactors as a moderator, the fuel is enriched fuel. Okay. For natural uranium fuel reactors, the moderator is heavy water. Clear? Now we discuss different types of reactors. Okay, this is another topic in the Glasstone Sesonske book, different types of the reactor. So based on chain reaction, what type of chain reaction? There are two types. Chain reaction sustained by thermal neutron or slow neutrons. That reactor is called thermal reactors. Chain reaction sustained by fast neutron. That reactor is called fast reactor. Okay. In thermal reactors, there are many maybe there, but I will explain a few of them.